So there are probably three more topics I want to talk about before the midterm exam. Today I want to discuss coupling involving other nuclei, heteronuclear coupling, mostly hydrogens coupling to nuclei like fluorine, phosphorus, carbon, even carbon-13. I want to discuss a little bit about other heteronuclear coupling, carbon to fluorine and phosphorus. So that's one of the topics I want to discuss. The next topic, so there's three I want to discuss before the midterm. Next topic I want to discuss is dynamic effects in the NMR spectrum, processes that can occur slowly or rapidly. And then the final topic that I want to discuss before the midterm is just to go a little bit deeper onto carbon-13 chemical shifts and factors affecting them and use of tools to better understand chemical shift of protons in carbon, or at least help us understand. That'll set us up well for the midterm. And that really finishes up our sort of 1D topics. I always like to say that before the midterm, we have sort of basic topics. The only thing that we don't get in before the midterm is the nuclear Overhauser effect, and we'll get that both in one-dimensional context and in two-dimensional context. And then after the midterm, we'll move into a 2D context, and we'll start with the first problem set that basically just sort of has cozy and trickle in and maybe HMQC, and then we'll start to really use that in subsequent homework sets and develop proficiency. So that's kind of the roadmap for the course for the next, both week or 2 weeks up until the midterm, and then a week and a half up until the midterm, and then beyond that. So normally when I talk about coupling involving other nuclei, I always find the lecture a little bit packed and maybe a little bit too fast. And so I think I'm going to slow down. Also, when I talk about dynamic effects in the NMR, I find it a little bit packed, and I think people can get pushed really hard on it. So I think what I'll do maybe is, if it works out, I'll take three lectures to talk about heteronuclear coupling and dynamic effects in the NMR. I don't like to split lectures. I like them to be about something, but I think this may work out well. All right. So for coupling involving other nuclei, I wanted to give us a feeling of the J's involved, a feeling of the coupling constants involved, because we've calibrated ourselves very well on proton-proton coupling. And some of the heteronuclear couplings, well, particularly heteronuclear couplings involving just a single bond, but also heteronuclear couplings involving carbon to fluorine, can be a little bit surprising. So I wanted to start by maybe talking on what the J values depend on. And I'll list probably 5 factors, and I'll give us a couple of tables just from Silverstein where I've pulled them together in a single place. So there's a whole bunch of factors. One of them is the magnetogyric ratio of the nuclei involved. In general, remember, the size of the nuclear dipole determines its magnetic effects. So in general, if you have a bigger nuclear dipole, or in the case of deuterium, nuclear quadrupole, you're going to have bigger splitting. And we've already talked about one example of this, and it was kind of an interesting example when I presented it. I'd like to present it again because I think it's something that now we can really appreciate. So if you look at the H1 NMR spectrum of CDCl3, there's always a little bit of CHCl3 in it, for example, about 0.1%. So whenever you see a proton NMR spectrum in CDCl3, you'll see a proteochloroform peak. And in that H1 NMR spectrum, if the chloroform peak is nice and big, you'll see, and I mentioned this before, you'll see two C13 satellites, right? So the chloroform peak will be at about 7.26 ppm in the H1 NMR spectrum. And then at about 0.55% height, you'll see the two C13 satellites, and they will be 208 hertz apart. In other words, basically, these two are a doublet that result from the C13 HCl3 peak. So that gives rise to these two where you're split. And then your main compound, your C8, your main protonated compound, your CHCl3 appears in the center. So J1 in this case, CH equals 208 hertz. And I've already hinted at the difference, and I did want to come back to this. So in the C13 NMR spectrum, you will see at 77 parts per million, you'll see a 1-to-1-to-1 triplet. That's, of course, from the main part of your sample, C13D, C13DCl3, and the separation of the lines then is 32 hertz. So that's basically because the deuterium has a nuclear quadrupole. It can be spin up, spin zero, or spin down. And the separation of any lines then represents a product of the magneto-gyric ratio. And that's J equals 32 hertz for that 1-to-1 triplet. And that specifically then is a J1 CD. Of course, I'm using D and H2 interchangeably. And so the ratio of the the ratio of the coupling constants, I'll say J1CH here to J1CD is equal to 6.5. And ditto, the ratio of the magneto-gyric ratio, the ratio of the magneto-gyric ratios, magneto-gyric ratio of a proton is 26,753, and the magneto-gyric ratio of a deuteron, of a deuterium nucleus, is 4107, and it's no accident that this ratio is 6.5. I haven't taken it to either of them to more decimal points. Point is that for identical bonds, for otherwise identical nuclei, where one of them differs in J, then you're going to have a much bigger J for the bigger magneto-gyric ratio nucleus. So that's one of the factors. So very low magneto-gyric ratio nucleus gives rise in general to smaller coupling constants. But of course, that's here we literally are comparing, well, not literally, but we are figuratively comparing apples and apples because we're comparing protons and deuterons that have the same type of bonding. The two isotopes have the same type of bonding. Okay, another factor involved, the number of bonds. So if you imagine you have W, X, Y, Z, if you're dealing with one bond couplings, J1 is generally very large. And I can show you numbers that are smaller than the range I'll give you. I can show you numbers that are larger than the range that I'll give you. But I'll give you a range that's sort of centered around 100. In other words, let's say approximately 30 to 300. In your textbook, you'll see an example that's 700. But the point is, you're somewhere on the order of 100 hertz. That's big, because that means if you're seeing a one bond coupling, those nuclei, those lines may be so far apart that your eye might not even think of them as being together. And I see this often with newbies in my group, with new people in my group, when they take an NMR of a trifluoroacetate salt, and the trifluoromethyl group, the CF3 carbon in the C13 NMR, if they take a C13 NMR, is a quartet, but the lines are so far apart that they're, over a ppm apart, and people may not initially recognize the pattern of a quartet, particularly since the outer two lines are going to be a third the height of the inner two lines. All right, for two bond couplings and three bond couplings, you might think that there would be very big differences in the J values, but we've already seen in the case of hydrogen that a typical three bond coupling might be for hydrogen-hydrogen. In other words, if you have a hydrogen here and a hydrogen here, that typical three bond coupling might be on the order of 7 hertz, but we've seen numbers up to 18 hertz and as small as 0. In the case of a two bond coupling, like the geminal coupling we talked about in phenylalanine, a typical coupling might be 13 or 14 hertz. So if you want to compare 14 or 13 to 7, there's not that much difference. Furthermore, we talked about how hybridization affected those, and we talked about, say, a terminal carbon on an alkene, on an sp2 carbon, where you had a double bond to a CH2, and we saw that our coupling constant was only a couple of hertz there. So both J2 and J3 are generally, not more than 20. I'll show you, I'm trying to give you a general example. I'm about to show you 47 as an example. But if I'm giving you sort of numbers that you can think about as ballparks, as very rough ballparks, as I said, you could go out of this ballpark by a factor of 2. Here we can go out of this ballpark by a factor of 2. But for both of these, 0 to 20 hertz might be the sort of number to keep in mind. The other thing that's interesting, as we saw, some of these are highly variable. We saw with the terminal alkene that J2 is very small. We've seen or talked about with dihedral angles that are close to 90 degrees, that J3 can be very small. So the other thing here, and it's not going to affect anything you do, is that often our J2 is negative. And negative only has to do essentially with, if I have something like this, it has to do with whether this line is associated with this line or whether it's associated with this. It has to do with the transitions. So as far as you're concerned, being negative won't affect you. The only place you might see some effect is in a certain type of cozy spectrum called a cozy 45 spectrum that can give different shaped cross peaks as a subtle indication of whether something is two bond or three bond coupling. Okay, so third factor I've already mentioned is geometry. And so particularly I'll put this in a finer point and say particularly dihedral angle. And a general rule of thumb is good overlap leads to a bigger J. And conversely, bad overlap leads to very small or no J. You know, we talked about the Karplus curve. If you have a 90-degree dihedral angle, you're going to have essentially no coupling. If you have an anti-periplanar relationship, you'll have a very strong coupling, very big coupling constant. If you have a syn-periplanar relationship, you'll have a big coupling constant. If you have a gauche relationship, like equatorial or equatorial axial on a cyclohexane ring, your J will be small. And we saw real implications of that, where when we talked about on a cyclohexane ring an anti-periplanar relationship from some stereochemistry, we said we expected that to be a big coupling. When we expected to see a gauche relationship, we expected it to be a small coupling. So even without doing anything fancy, we could predict, oh, this peak will be primarily triplet-like, this peak will be primarily quartet-like, and then there'll be smaller couplings superimposed on it. Thoughts or questions at this point? Now, some of the implications of what I'm saying here are interesting, because as we move along in the second half of the course, you're going to find the technique of HMBC to be very useful. Heteronuclear multiple bond correlation spectroscopy. And that picks up 2 and 3 bond CH couplings. It's very useful for putting the pieces of the molecule together. But some of the limitations are it's going to pick up both 2 bond and 3 bond couplings. So the first caveat is we won't know exactly which bond, you know, how many bonds there are between the 2 atoms. And if you have poor overlap, meaning like a 90-degree dihedral angle on a 3 bond relationship, you may not pick up that coupling at all. It's James's favorite statement, absence of evidence not being evidence of absence. This is going to make more sense when we start to need and use HMBC, and we see both its power and its limitation. All right, so I mentioned 5 factors, so let's talk about additional factors. Hybridization. So more S character in the bond generally leads to bigger J values. And the example I'll give as an example of that you've already seen is the trans coupling on an alkene is about 17 hertz, but the anti-periplanar coupling like H-axial to H-axial on sp3 carbons in a cyclohexane ring might be 10 hertz or maybe 11 hertz tops. So more S character in the bond makes a difference. Other factors, for example, and I'll just sort of lump things together, but such as electronegativity. And we've already seen a little hint of this in some of the spectra we've looked at. I think we've seen it already. But for example, normally I say that when you have a typical coupling constant. It might be 7 hertz for a typical sort of coupling constant. This coupling in an acetal is ever so slightly smaller. This coupling might be on the order of 5 or 6 hertz versus, say, this coupling here that might be on the order of 7 hertz. And what you'll end up seeing if you see these methyls as quartets and your eye sort of calibrates on the spacing of the lines of this plain vanilla methyl quartet here, I'm sorry, if you see this as a quartet and this as, if you see, let me start over, if you see this methyl as a triplet and you see this methine as a quartet, your eye calibrating on the line spacing of this methyl says, oh, this is about the distance that 7 hertz is. And then you look at this quartet and you say, oh, that seems to be a little smaller. And it's just this little thing in the back of your mind. For a single electronegative atom, it's not going to have a big effect on J, but for at least oxygen. But by the time you have 2, it can have an effect. So that's an example of other factors that you've seen and we will see again. I think I flashed over that when we talked about diastereotopicity. Let me give you some typical values and then we're going to start to look at some real spectra. So fluorine is another high magnetogyric ratio nucleus. It's not quite the same as a proton. I think it's 25,000 and change as opposed to 26,000 and change, but it's big enough. It's quite big. And fluorine has very different bonding. Carbon to fluorine has very different bonding than carbon to hydrogen. So we're not comparing apples and apples. So if we consider hydrogens here, and hydrogens here, so this would be a 2-bond hydrogen-fluorine coupling, J2HF. Those are big, really, really big. Let's say 44 to 81. I'm about to give you a table from Silverstein where I've abstracted some of these values, and then I'll give you an Aldrich spectrum. So bigger than just about any sort of 2-bond coupling that you would expect. And it can be surprising in the NMR spectrum. J3HF can be big as well, 3 to 25 hertz. What's interesting is fluorine is a little bit different. Normally, we don't pick up a whole lot of bonds over 3, except, with intervening double bonds. We don't pick up a whole lot of couplings over more than 3 bonds for sp3 carbons. But you may see a small coupling, we'll say 0 to 4 hertz. The other case that's a little surprising, and you'll see this on the homework, is fluorine on benzene. And so if we think about our ortho, meta, and para hydrogens, it probably wouldn't surprise you that your J3HF for ortho, that's synonymous with ortho, is on the order of 6 to 10 hertz. And you'd say, okay, that sounds just like what we expect for an ortho coupling for hydrogen to hydrogen. But you're used to a meta coupling being, say, 1 to 3 hertz for hydrogen to hydrogen. The meta coupling is big compared to what you would expect. So the J4HF so that's our meta. That's on the order of 5 to 6 hertz. So think for a moment about the implications of that. If this were, say, just a chlorine over here and there was no spin-spin coupling, if assuming first order behavior, assuming first order analysis, remember this ring system without the fluorine would be an AA prime, M prime X at best. But assuming that it was first order like behavior, you'd say, oh, this hydrogen should be split by one big J and one small j. In other words, it should be a doublet of doublets or something that looks like it. This hydrogen should be split by two large j's. In other words, an orthocoupling here and an orthocoupling here. So it should be triplet or maybe doublet of doublet likes with two very, very similar j's. But with the fluorine over here, rather than say a chlorine, oh, and you'd expect some, well, no, you wouldn't expect metacoupling, although it would be non-first order. With a fluorine here, this hydrogen is now going to have a still pretty large coupling to fluorine. So it's going to really surprise you in the sense that you're looking for something that's first name should look like triplet or have two big J's in it. And there's going to be another big J. And you'll see examples of that in the homework. I guess the other thing that comes up is the para-coupling. And so normally I've said for protons, we almost never see a para-coupling. In other words, if we have a hydrogen here, we almost never see a para-coupling. It's usually less than about 1 hertz, and you tend not to be able to pick that up. And one example was a particular relationship, I think it was the 2,5 positions of pyridine, where often we could get a slight para-coupling of maybe 1 hertz. But here, it's about 2 hertz. So as you go on to look at some of the patterns in the homework that you see for fluorinated aromatics, you're going to find things to be a little bit surprising. Thoughts or questions at this point?
I guess in cases, I think, do you have any tips and tricks to be able to identify between like normal proton splitting versus proton fluorine splitting, aside from constant, I guess?
If you know that there's a fluorine in the molecule, I would say expect proton fluorine splitting. I guess your question is sort of, if you didn't know what the molecular composition was and you didn't know what a fluorine was, could you tell? And I think we're going to see a couple of examples where the answer would be yes. And I come to pattern recognition here. So let's take a look, and we'll see 2 examples here, and I want to show you in those examples sort of things that might surprise you, but particularly the second one we look at, I think will be a nice clue on that if you're good at, if your eye is calibrated to patterns. Other questions? All right, let's start with the handouts here. All right, so this is just the second page of Silverstein's Appendix F, which I think so highly of. And this basically has the same information I wrote on the blackboard with a little bit more about some phosphorus hydrogen couplings. And you see on your table here, you see that one that I was mentioning is often very big. Silverstein has a wealth of information, sometimes scattered in various appendices and tables. And I think a little later in the handout, I give you a couple of more tables from Silverstein. All right, what I wanted to do was start with this very real example of triethylphosphate. And the reason I thought this would be a good example is people often use phosphorus compounds in Horner-Wadsworth-Emmons reactions and in Wittig reactions. And so we look at the NMR spectrum of the triethylphosphate, and this is just the Aldrich NMR spectrum. So all of these H1 NMRs that you can find yourself on the Aldrich website are 300 megahertz H1 NMR. And then you have the carbon NMR spectrum taken on the same instrument. So it's the same 70,500 Gauss magnet. And those are 75 megahertz carbon NMR spectra. So in the NMR spectrum of triethylphosphate, we see a nice big typical methyl triplet, no great surprises there. And then we see a pattern here that at least on first glance, you might say looks like a quintet. So you might describe it as an apparent quintet. It doesn't quite look like a quintet, but you might say, oh, it looks kind of like a quintet. What's going on with this peak? Let's take a look. I've expanded it over here. Can someone help me out with this?
Might this be a doublet of quartets?
Ah, yeah. It's so it's a doublet of quartets. And Franco, can you explain why it's a doublet of quartets or how you see it as a doublet of quartets?
I was just thinking that like maybe is this well I just kind of figured that like the rightmost peaks of the first doublet and the leftmost peaks of this, or so the rightmost peaks of the first quartet and the leftmost peaks of the second quartet kind of like overlapped to give the signal. I didn't really look at the Hertz coupling, which is probably the one to look at for the best evidence, but yeah.
So you're starting to see them just ever so slightly separate.
Yeah.
And you notice the heights of these lines kind of match up to one. I should pick a different color here since I'm doing a lot of writing. So we kind of match up, if you squint, to 1, 3, 3, 1, and then here 1, 3, 3-ish, 3-ish. I'm sorry, 1, 3, 3-ish, and 1 over here. So you kind of can see this splitting going on where you've split and they're ever so slightly different. Can you, Franco, extract out the J values here? Can you read? I've given us a ruler. Can you read the J values off? What's the J for the quartets?
The J in the quartets looks like 8 Hertz about.
So if I draw a line.
So between the first, oh, sorry, but between the two quartets.
Let's start with within the quartet.
Oh, within, okay, yeah.
So what do you see over there?
Yeah, that one's about 7.
7. And then the 8, I think you're talking about is this distance. Is that what you're talking about?
I was looking between the distance between like the 30 and the to the leftmost and the second to leftmost.
So 30, so from here
Yeah.
to which line?
To the second line.
To the you mean this one here that I've labeled as 1?
That you labeled us as 3.
As 3.
So that one actually looks maybe more like 7, 7.5. So
yeah, 7, 7.5. So if we do our splitting tree and we have only a very slight difference, and it's hard for me to calibrate it in my drawing, but maybe a little color will help out here. So if I split over here and I split off, I guess I'm not great at drawing this out. But basically what I would be getting would be, I'll try to use some color. We would be getting 1, 3, 3, 1 here. I'm doing a lousy job this morning. And we'd be getting 1, 3, 3, 1, and that's what we're seeing. So it's a doublet. So what we have here is probably best described as a doublet of quartets, J equals 8, 7 hertz, where the smaller splitting is 7, the bigger is 8. And those numbers, of course, are just read to the nearest unit as best as I can on this scale. But that's some guidance here in terms of what we're seeing. Now, what is giving rise to this coupling, right? So this is our CH2 group here. And it's next to a CH3 group. And so this coupling here is 7 hertz. And we're next to a phosphorus over here, a phosphoryl group. And this coupling here, the heteronuclear coupling, is 8 hertz. Thoughts?
So I think the quartet splitting comes from the methyl group.
Right, the quartet, basically this makes our Q splitting, and then the 8 hertz makes up the D splitting. So this is our J3 pH, and that's our J3 HH. And if you hadn't been able to resolve it out, you could have said, oh, it's an apparent quintet. J equals about 7 hertz. And that would be a reasonable analysis too. We're sort of right on the cusp here. We can just see sneaking under here, just teeny evidence of the further splitting of the difference in coupling constants. Additional thoughts or questions on this one?
James, would it have been a quintet if the J's were the same? Is that why?
Absolutely. Absolutely. If the J's were the same, it would have been a perfect quintet. If the phosphorus hydrogen coupling had been just a hair smaller, you would have quite legitimately said quintet. And even so, if you called it a quintet here, I'd say, even if you didn't say apparent quintet, because it looks pretty much like a quintet, a little off in the line heights. It's not quite the 1 to 4 to 6 to 4 to 1 that you'd expect for a quintet, but I'd say, yeah, that's pretty reasonable.
James, out of curiosity, I made this splitting pattern in the Excel spreadsheet. Would it be possible if I shared my screen just for 10 seconds to demonstrate?
Sure, that would be great.
So this is the doublet of quartets that we observe, sorry. 1 8 hertz coupling and 3 7 hertz couplings. But if you pay attention, when this changes to 7, which would give us the 7 hertz quintet, those peaks resolve into the quintet. But if we were to go back to 8, you see the very slight overlap between these two middle peaks and then the shoulders of these inner peaks also. So this is a useful tool for visualizing these situations where the coupling constants are very close to one another.
Now leave that up for a second, James.
Sure thing.
So what I've done in writing this spreadsheet was I put in a typical line width that's the product of relaxation times, and we'll be talking more about that in dynamic NMR, as well as the limits of magnetic homogeneity and digital resolution. If the peaks were a little bit broader, you can put in 1.5 or 1.7. You probably wouldn't see things resolved at all. And if they were a little sharper, and maybe you can put in 0.8, you'd see them better resolved here. So that really reflects sort of the limits of both the spectrometer and the physics of the uncertainty principle. Other thoughts on this? So I want to look at the carbon NMR spectrum now. And the carbon NMR spectrum, you can kind of see if you zoom in really close here. You can kind of see that we have a doublet for this line, and we have a doublet for that line. In other words, those two carbons are split into doublets. And you can see that on the peak printout here, where you see two lines, one at 63.64 ppm, and the other at 63.56 ppm. And then here a pair of lines at 1619 and 1610. So those are in turn reflecting our phosphorus coupling. So the line at 63.6 is a doublet, and our J is a J2 PC. And if I want to calculate that J, it's 63.64 minus 63.56. So it's 0.08 ppm. But remember, we always report our J's in hertz because they're invariant in hertz. So at 75 megahertz, 0.75 ppm times 75 hertz per ppm is equal to 6 hertz. And so this is a doublet J equals 6 hertz, and that's our J2 PC coupling, and we would report it as 63.6 parenthesis doublet J equals 6 hertz. By a similar token, if we do the same math for the peaks, for the pair of lines at 1619 and 1610, for our peak at 16.1, we would end up with, and remember that's 16.19 and 16.10, if we did that same math, we would end up with 7 hertz. And so this reflects our J3 PC coupling. And so that 16.1 is a doublet of J with J equals 7 hertz. Normally, you would report your coupling constants to the nearest 1/10 of a hertz if you can, but you'll notice here, because my peak printouts aren't more precise, I can't get more than one significant figure. And honestly, that's probably pretty reasonable for a C13 NMR spectrum. So that's an example of phosphorus carbon coupling and phosphorus hydrogen coupling in a very sort of typical ordinary compound. So I want to come next to our next example, which is fluoropentane. And again, I've just taken this from Aldrich and pulled out the spectra. And so if we look, the first thing we notice over here is there's a pair of triplets. And if you didn't know there was a fluorine in the molecule, you might say, oh, there's 2 triplets. Look how much they look alike. And maybe the second thing you'd notice over here is, wait a second, we also see a pair of twins over here. And you might start to realize something is up. And particularly if you then looked at the C13 NMR and you said, oh, that's interesting. We have 2 lines here that look like twins and 2 lines here that are so close. And even this peak here is split into 2 lines, where you'd see that over here. And you'd see these pairs of lines that look like they go together. So you might get an idea that something is going on with your spectrum. And you might realize there's a fluorine, or perhaps you would have known you had a fluorine in the molecule. And you'd say, oh, wait, that's not 2 triplets. That's a doublet of triplets over here. That doublet of triplets, I could read the distance of the triplets, and it's about 7 hertz. And I could read the separation of the triplets, and that's about 47 hertz. That's a doublet of triplets, J equals 47, 6 hertz. And if I had a better printout, I could probably read it to the nearest 1/10 of a hertz. And so that is reflective of our 2-bond coupling. So that's our J2HF. And even if I couldn't quite characterize this pattern here, this doubled up pattern that we're seeing over here, you could say, well, it looks like it's doubled with about a separation of about 24 hertz. You could see, sort of drawing a line down to the scale here, drawing a line down to the scale. Those are your beta hydrogens. Those are the hydrogens over here. And you'd say, oh, okay, that's our J. So I probably would just characterize it as a multiplet, but you can see embedded in there is our J3 HF, and that's 24 hertz for our 3-bond coupling. And if you applied the same type of analysis to our carbon spectrum, and you looked at this peak here, this doublet here, and this doublet here, you would end up with an analysis that said, oh, okay, so now we go ahead, we look at the separation of the lines, and here our peak at 84.1 ppm or 84.2 ppm is a doublet, J equals 167 hertz. And that's our J1 CF. And this peak here has that about 30 ppm or 30 point, I think 1 ppm, 30.2 ppm. That's a doublet with a J2 of 19 hertz. And if you look at that last pair of lines, that looks like we're seeing our J3CF of 6 hertz. So all of that is embedded in these ordinary spectra that we are looking at. Thoughts or comments at this point? All right. Well, I think what I'll do next time, as I hinted at, is we're going to continue and to give you a preview of some of the things that you're going to see. We're going to look at a compound that has 2 C13s and a phosphorus in it that I've pulled out, and we'll see some really cool coupling patterns. And then I think we'll move on to start talking about dynamic effects in the NMR. So if that's it for today, I will take any last questions, or else send you off on time, or more or less on time, to your next class.